Before we start, here are our electrical schematics and a sample calculation used for our hardware. To see the status of our code, users need to enter a password into the serial monitor, as shown here. Now it's time for the demo. So here we have our traffic light sequence, which follows the states as shown here, as well as the serial monitor reporting the current state every 2 seconds. And here's a demo of our adjustable traffic light and pedestrian LEDs. Now onto how our system operates.
Before the program code, global variables are defined and the setup function initializes the serial monitor and pin modes.
The loop function starts off with monitoring the button state and stores it inside the variable button pressed. Then the program begins at its initial state. Serial monitor function is then called to display the reporting of the system, and the analog value from the LDR is read. Additionally, variables for time intervals, countdown, and states are initialized. Inside the while loop where the button is pressed, the program enters a state machine that transitions from state to state based on the elapsed time and its conditions. This if statement is to check whether the button has been pressed or not. If pressed, it returns a value of 1 and otherwise returns a value of 0. The state machine code block is operated when the button pressed is equal to 1 in the while loop. In cases 1 to 3 and 7, it performs time-based tasks using Millis function for controlling the behavior of pedestrian and traffic lights by calling corresponding functions, state 1, state 2, and etc. Throughout the execution, when the condition of the time interval is no longer met, the state of the function is updated by 1, meaning that the next case is performed. When a time has passed for state 4 to be executed, state 4 function is called to control the behavior of lights and prints out in the serial monitor. The numRite function is then called to display the countdown. After 1000 milliseconds of the countdown display, it increments each digit value by 1 and time is resetted for the next SSD update. Another if statement checks if countdown is less than 1, setting the state to 8 where all segments of the SSD are off. This is a similar case to state 5. Case 6 contains the calling of numRite 10 to display that all segments of the SSD are off after the countdown has been completed. Case 8 represents the final state of the state machine where the traffic light sequence is complete. The SSD is set to numRite 10 like in case 6. A 3D array declared as an integer is defined to represent segments to control its on and off states corresponding to a particular digit. Each row corresponds to digits 0 to 9 and each column are segments A to G. To control the display of the countdown from 0 to 9, the numRite function takes an integer num as a parameter representing digits to be displayed. This controls segments A to G to set either high or low representing the corresponding digit.
An if statement checks for available storage in the program through the serial available function. If there is available storage, the variable user input is then set to read the user's input through the serial pass int function. The password input function checks whether the user input variable matches the variable called password, and if true, sets a predefined variable serial monitor off to false. If serial monitor off reads false, the serial monitor function is executed. The LED's brightness are controlled through the int function LDR brightness. The variable sensor value reads the raw value of the LDR through the analog read function. The map function is then used to scale the LDR values from 0 to 1023 to 0 to 255, the appropriate range for an LED. This scaled value is set to the variable brightness, which the function returns and is then called when turning the LEDs on or off. The serial monitor function prints out what is happening in the sequence, as it reports the state of the pedestrian and traffic lights and the raw LDR analog value. Millis is used as a function that allows multiple tasks to happen concurrently, unlike delays. In this code, if current time set to Millis is divisible by 2000 with remainder 0, our serial monitor prints. Series of state functions are defined so that it is called inside the loop function. Each state function sets the state of all lights and the brightness of each light. These functions work similar to a bool statement, returning a 1 or 0 whether the light is on or off. Similarly, the button state function reads whether the button has been pressed or not by passing the digital read function of the button to the button state function. These functions are then called to the serial monitor.
There were many challenges that we faced in this assignment, those of which included the serial monitor reading the incorrect state, the pedestrian LED not blinking at state 5, as well as our button running on its own. There were many aha moments during this assignment. One of these was when we were trying to figure out why the RGB was not turning on. We realized it was because the LDR function was not called properly due to it simply missing its brackets. For this second assignment, we implemented switch cases which made the code easier to read, as well as arrays which provided an alternate to using functions when it came down to coding for the SSD. Furthermore, the analog read-write functions were used to allow input of continuous data rather than the digital read-write for the discrete high-low from assignment 1. It was easier to work on this assignment as a team, since it was easier to bounce ideas off each other when it came to coding, as we were able to combine different ways to code for